Hello everyone, am I audible? Okay, so let's start the session now. Let me present my screen. So today's session is for week 11. I hope my screen is visible. Okay, so today's session is going to be very interesting. Okay, we are going to see about the function. Function is already you have seen what is a function. Okay, I think in week 1, yeah, just introduction. Then you have seen the sequences, all other. So in week 11, you are going to see what is a function and their characteristic. Okay. And then a very specific function which is called rational function. Rational function. And then a bit about the trigonometric. We have seen the sine function. Okay. Today we'll see them some other trigonometric function cos, tan, sec, cosec, and their properties. And also we'll see the inverse trigonometric function. I'll try to cover till lecture 5. The remaining will be covered in the next week. Okay. So before to start, I want to know anyone have any doubt, any kind of doubt? Want to say something, discuss something? Then we'll start the session. Any suggestion? Anything? Okay. So again, a request to all of you that whenever you are going to say something, better to unmute yourself and then tell in place of giving the thumb impression or writing in a chat. It's always preferable if you unmute yourself and then speak. Okay. So that I will be also get motivated that all of you are understanding and communicating with me. And so many effects are, once you speak with the teacher, um, so that impact on teacher also, he will be more engaged in comparison of you. if you just give the some reaction. Okay, if you speak that, then that would be more engaging. Okay, so try to speak. That would be really good and helpful for me to discuss with you in a more better way. Okay. So, so all of you even started looking first week itself that what is a function. So function is nothing but very simple. It have given as here it is. I will go with that as in the lecture. So function is nothing but it would be a kind of expression is given, and we'll discuss. So let me write here week 11. Okay. So function. What is a function? So here in Maths 1, yes, we didn't see the set theory, so I will not start with the definition of that. Otherwise, function have very broader meaning, not broader in the mean to say some different meaning the set theory. Okay, that is saying to be it started or even started from sex theory and some relation kind of thing. It started from relation and then some definition is developed. But here we will start with the simple expression that okay, some it could be of this case, and the notation of the function is like this. Okay, f, or it could be f1, g1, okay, g2, or anything. I mean to say within this middle here the bracket, within the bracket x should be there, and some expression is given. So we are going to study the only one variable case here. So some expression, it's depend on even very vague also. Okay, or let's say some expression I'm giving some of this case here. So vague in the sense of I'm giving this one, which is a vague. No, you don't know the meaning of it. What is it says, but whenever it's given, so it's needed to define it. What is the meaning of this sign? So this is floor function. This is a floor. Whenever you are giving 2.1 and then if you are finding some, let's say I am giving x is equal to 2.5. That means, or let's say here I am substituting here in this function, I am substituting to in place of writing x, I am writing 2.5. It means that where is a x, I will substitute 2.5. So this is an expression, some expression is given, but which is a implicit. So function is a kind of some expression would be given, but it would be given as a implicit, sorry, yeah, implicit or explicit. Okay, some would be generally given explicitly, proper expression. I just given a very different and vague. Generally, you have seen this kind of expression. Okay, fx is equal to, let me write here separately, fx is equal to x square plus 2, or maybe x cube plus 5 x square plus 2, maybe of this case x plus 5 upon 2x minus 1. In this case, this all or some expression would be given, expressed in the terms of x. So whenever you are getting the value at some particular point, or mean to say you want to find the value of this function at point, let's say x is equal to 2, then whichever you are going to consider the expression. Okay, yeah, let's say I am considering this expression. So f of 2 in place of x, I will substitute 2. So inside here I am substituting 2. So in the expression also I will substitute. So here this is going to be 2 square plus 2, which is close plus 2, and this is 6. So here I have started with this very implicit. I said that this meaning of the floor function is that a kind of this one, in place of x I'm substituting 2.5. The meaning of this sign, which is a floor, means this is going to be 2. Okay. So here finally f of 2.5 is going to be 2. Okay. So or let's say you have a 3.1, the floor of it going to be 3. So it means that this represent a greatest integer value less than or equal to that number. That is the meaning of it. Ever you have seen it? Okay. So function is a kind of that. I'm not. I will pleased to hear from you that is this understandable or not, or maybe you want some more comprehensive definition or some more example, if you just let me know, that would be very much helpful to me, that you are understanding. Or you want some different definition of the function. There are so many definitions. You know, if you know it something very differently, you can tell me also here in the session. That would be really good. So anyone else want to say something on this? So what is the yes? Yeah, you.
No, it's clear, sir.
It's fine, sir.
Okay. So function is here, just we are going to with the expression. So some expression would be given, based on that we'll evaluate the value. The different meaning came. So this is so compute the function and plot it. So there is a meaning of plotting also. So plotting of the function, let's say I want to plot this function. I am considering fx is equal to, let's say, x cube plus 5x square plus 2. Okay. So plot, I mean, I'm not sure where it, how we'll do this, but one thing you can do, you can means if you want to graph it, plotting means you will give here. So give your input. So here, this is your x-axis, and this is your fx. Okay. So whatever, let's say here, this is 1, this is 2, this is 3, okay? This is 4, this is 5. So in what, so here I am substituting 1 in that, and whatever I'm substituting in place of x, I'm giving in place of x, I'm writing or substituting 1. So it means that's 1 cube plus 5, 1 square plus 2. Okay. Now, so here this is going to be 1 plus 5 plus 2, which is, 7 and 8. So this is going to be roughly somewhere 8 here. So like this, I can evaluate the value at 2. Okay. I can get here 2 cube plus 5 into 2 square plus 2. So it will be 8 plus 20, right? And then 2, this is 10 and 30. So here somewhere would be 30. So like this, as 3, it is going to be somewhere. At 5, it is going to be somewhere. So it is very much sure that it is going to be more and where more value, as it is very much clear there is a x cube and x square. So that means a graph roughly could be of this one, maybe more of this case. Some turn would be there, and also it could be of this one. It will be some like this. So how I am getting this? I am getting because of, I got the idea, means when I'm substituting, it is kind of, it increasing values here. This is going to be less than, slowly it decreases. So this is how, means I am plotting the function. Okay. So how, what is the plotting of it? A plotting meaning is that I'm giving the input, I'm noted here on the axis, and output I have noted accordingly. I noted here accordingly. Let's say I noted here, somewhere is there, and I just scratch or matching with them. Roughly, I substitute integer. Even I should to substitute any rational number, irrational number. Know it. What is that? And according to that, I plot. But getting the value with respect to irrational, it is going to be tough. So I just roughly approximate it. Okay? I just roughly approximated. Okay, at 3 it is going to be this. At 4 it is going to be this. So this is the meaning of plotting. I will just going to give a test tool of. I am going to give a tool which maybe you have seen earlier. I think professor sometimes use it also. There is a tool which is called Desmos, okay, which is a graphical tool. Desmos. This is a graphing tool. So how many of you know about it? Heard about it?
Yes, sir.
Yes, sir, we use that.
You use, right? No?
Desmos as well as GeoGebra. Yes, sir.
GeoGebra is also very, that is even more comprehensive. That is also, you can, this Desmos is you have seen for 2D, but GeoGebra is even give the
Yes, sir.
graph of three-dimensional plane you can draw easily. So our eyes can visualize up to three-dimensional, which GeoGebra does. We cannot visualize the 4 dimension, so that is not there. So till 3 dimensional we are able to visualize. So GeoGebra that much help us. But Desmos is mostly for 2 dimensional, and here we can graph easily any function. And what is the intrinsic behind it? It is doing the same work as we are doing, but it is doing on the computer. Some Python code would be written, or maybe on the something other. You are able to see this interface, but behind it, it is of kind of loop is happening. It is always give some value at place of x and collect some value output. Okay. So even see, I wrongly draw it. Even this is of this case. This is what our function which I started plotting it. Okay, it would be a bend here and it would be a bend here and then back to here, and we'll go to the negative infinity. Okay, so this is doing the same thing. See, it is at particular point it's evaluated the value. So this is how, if you zoom it, no, continuously zoom it. Ever you try to zoom it, if you zoom it, it will be give, it is a kind of this one, but it have also a limit. Okay, if you start zooming, it have some limit. Till that it will be evaluated. It will evaluate the value. After onward, it will not zoom in. There is a picture, when you do BSc in maths or maybe some higher, there is a fractal word is there. So in fractal is that what if you zoom in, zoom in, zoom in, if you continue will do, it will get the same structure. It will not change. You can somewhere change what is a fractal. So, but this is not a kind of that. If you zoom out, zoom in, it has some limit. Okay, it will apart from that, it will not going to zoom. Okay, but it is going the doing the same meaning. So sorry, same work. It's giving some input and collecting the output, and according to that, it's graph. Okay. Sometimes calculating value is going to be tough. That's why these tools are very much helpful to understand, so that whenever this is a best to do practice yourself. So let's move ahead. So this is about some graph. Okay. So there are some word increasing, monotonically increasing, monotonically decreasing, or different functions. See, this is a kind of sigmoid function. He is saying this function 1 upon 1 plus e power minus x. The professor using the Desmos same, and is saying that okay, as you move on to negative side, it will be we have like asymptote, and positive side it will go to infinity. So asymptote for x-axis here, value is going to be very close to 0. So these are some function you can even want to see it. I think derivative we have already done. If you see the function 1 upon 1 plus e power minus x, okay, you want to find the value at 0. So at 0 here, or maybe you want to find the value, or the finding the limit as x goes to infinity, very large number. Oh, hope all of you know what is the meaning of infinity. We started from also. Here this means that this sign means you have a very large, very large positive real number which you cannot expect. What is that? So this says that you are giving the input, in the function very large. Okay, but it is not fixing that which large number. So it says that when this limit means, last time I told you, this limit is a kind of you are driving or you are riding a bike, and I said started you know that if you take the full accelerator, if you have a hero bike, you take full accelerator, will not go beyond of 100. It will be at most how whatever accelerator you will take, it will go till infinity. That is what he says. So let's say I'm in place of infinity, I'm writing full accelerator. Okay, full accelerator I am writing. So in that case, this at most function value is going to be 100. The speed is going to be 100. That is what the limit meaning. Okay, the word itself says the limit. If you whatever input I will give, it will not go beyond of that number. At most 100, it will go as the hero bike I am saying. The same meaning is there. The real meaning of the limit. Okay. So as it will go, x goes to infinity, it will go, it become very large, so it will go to 1, I think. Okay. And it will go substitute minus 20, it will go to 0. So even if you have the idea derivating, you have done it already. Either you know the property of it, e power minus x. It is an increasing function. No? We have seen the e power x. So if you are going to substitute very large number, this is going to be very small number. And this is going to be small. So this is 1 upon 1 plus very small means around to 0. Limit is there 0. And this is going to be 1. So slowly, no need to be do any kind of, in knowing the property of the function is enough to evaluate the limit. This is interesting. The limit is very, very interesting. Why? The reason is it will help a lot to understand or even to do many things. Derivative, integration. Integration is a kind of very, 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 very useful thing. That means, I mean to say, this is Riemann we started. No, Riemann we last time we have seen last Riemann is there. Riemann is nothing. Riemann is just a piece of region you are adding, and the thing is that you are making very, very small piece, and then you just added them all. So Riemann is nothing. It is as we used to uh, do the addition of the regions to get the whole region. So it is not different. So these are some idea. These are real idea. Okay, I hope you can relate to this maths thing. So these are just graphing professors with the different example is telling, and he's graphing that the function. All of you maths background, I hope you know, and you are feeling it bore also kind of, because all of you from 12 maths background, so function very much. So let's move ahead to the next topic. That is I don't think we have seen this because this is previously, it was in the older maths book, but now it is here because it is very much useful in our this electronic system course. It used to be available in the older book, rational function and their factorization. Okay. Maybe it is available in these days, and I'm not sure. So anyone have seen this? If you have anyone have gone through with the second lecture, anyone have seen this rationalization, doing the factorization of the denominator and making coefficient as lesser power in comparison of, or making the numerator to be a constant or some variable but lesser power in comparison of denominator. That is called factorization. That is a different name, rationalization, something name is there. Anyone have seen it in the 12th standard? Because all of you coming from
Yes,
mostly
sir.
Yes,
seen
sir.
it, right? This is interesting and easy also, not tough. So the idea is to, why we are doing it, to see some simple thing. Let's see that what are the things are there. So rational function are not easy. I have just given one example also, saying to be function. What is this kind of expression? The outputs you will get here as a rational number. So proper definition of rational function is, saying to be a kind of the here is in numerator it would be a polynomial, okay? And denominator also a different polynomial, okay? Polynomial 1, polynomial 2, okay? Let's say I'm polynomial saying to be of, let's say 3x square plus 2x plus 1, and denominator some polynomial I'm writing 5x cube plus 2x square. So let's say I'm saying the rational number f, the rational function fx. So properly if I will write, so your fx is nothing but 3x square plus 2x plus 1 upon 5x cube plus 2x square. So if you see the definition, it's professor started saying the numerator is going to be a polynomial and denominator is going to be a different polynomial, maybe of the same degree, different degree, or lesser than or greater than. It's depend on the how it could be. Means there could be a difference in the power or maybe same also. It doesn't matter. The important thing is that the numerator and denominator are going to be a kind of polynomial. Okay. So their graphs are very strange. The strange thing is just now we have seen. If you see it, I will try to graph that. This function. Let's say I am making this polynomial or maybe of this case. Let's say x or 4. So see the how strange it is. And if I reduce the degree, it will be it's look like very constant type also, or maybe see how it is very very strange. See how it is. So rationals are very strange. Oh, this is a power 43. No, okay, let me skip this one 3. See how it is. So these are the rational functions where the denominator and numerator are kind of polynomial. Okay. See the how much use you see it here written. Rational functions are used in IIR filter design and system transform function. It will be used in the electronic system. So whatever you are studying here, no, it is not. So this is one thing you can remember in your mind. Whatever the topics you are studying in Maths 1, you are going to study Maths 2. Those are directly going to relate your other courses in other courses, even in electronic system courses. Somewhere you will see these functions, these properties, derivatives, geometric series, or whatever things, trigonometric function, all other things are you are going to see either in Maths 2 course or maybe some electronic course. So geometric series is there, you know it. What is that? So this is one result is given that what his professor is saying, assuming to be a series of 1 upon 1 minus x, could be written as 1 plus x square plus x cube plus kind of this one. But we can use this geometric series to get the series of this one. This is one use of doing the rationalization here. So you can take common, you can make this a as a 1, and you can write x as x by a, and assuming to be x as a x by a, and expand on that, you will get the same. That is one use is saying. Okay, this is also good idea. No, sometimes if you remember, this is one very good idea. Sometimes getting the series is stuff, but if you remember this series, you can convert any kind of this to be in a series form. This is the good thing in maths. You have seen, I hope you have seen it. Let's be on the topic, and whatever we want to do, let's do that. Let's be on the topic. So here is what is the meaning of it. So we are studying this rationalization to get off this kind of. Can we are we able to write like this? C upon this one, some something here, some d upon something is there, then e upon something is there. Yeah, are we able to write, or we are able to do like this? That is what here we are going to next see. And professor is giving the proof. Yes, this is true. Why it is so? Proof is there. Like there exists a constant c1 of such that you can write if numerator is this one polynomial and denominator is this one. Okay. So see that what is the degree of here? The numerator is x to the power k minus 1, and here what is the degree of the denominator? Just k. Numerator degree is less than or equal to k. Okay. Whenever the numerator degree is less than or equal to some the denominator degree, in that case it could be factorized, or like this we are able to write in this fashion: c1 upon a1 x plus c2 upon a2 minus x plus dash 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 ck. So we are able to write it. So whatever the proof is there, that is giving itself a idea how to convert. Okay. So for example, I am taking an example from the lecture itself. Let's say I am taking this one. Okay, unique complex root is there. Okay, let's say I am taking x minus 1. So let's say x minus 1 upon x plus 2, x square x plus 1. Okay. So, but we want to convert this to in this fashion. Some c upon x plus 2 plus t upon, let's say it's going to be, I'm going to keep the same here, this one, in this fashion. So how we'll get this? So assuming to be, let this is what it is. Let this is equal to this. So you can write this one as c. So you can multiply, you can do this polynomial multiplication. You can do this is x plus 2 and x square x plus 1, and c time x square plus x plus 1 plus d up into x plus 2. Assuming to be this, let and then proceed with this and taking the right one as the same. Now it is like that you are solving this. So so it is not good practice to cancel it out. This is not the good thing, because even if you are assuming it, this is non-zero, even anyhow we are going to take it non-zero. So even let's say I'm doing the cancel it, because here is x is not going to be minus 2, and here is whatever the root is coming, not going to be, assuming to be that on. So we can cancel it out. This is x minus 1 is equal to, here is c x square plus cx plus c plus d of dx plus t. Okay, so here is, if you compare both side degrees, this is a constant, this is a constant. So dx minus, so here is d, so here it is also the cx and cx, dx is there. So you can write cx square plus c plus d, okay, and x plus c plus t. So it means that c plus t is equal to 1, right? Here is the coefficient is 1 here, and here is 1. and C plus D. I think I'm making mistake. It's -1. That is why we are getting a very different thing. Yeah, so here is I missed that. If it is of degree 2, then we have to keep x as denominator is this one. So it is a very simple. When I started this here, see this is a degree 2, so I missed that. We have to keep of this case, so it is already breakable. Okay, so either I should to make it like this. This is going to be cx upon this case. So here it is of c upon x plus 2 plus d upon dx upon something. If it is degree 2, then we'll keep here the dx. X is going to be there. So professor is doing on some example very clearly. You see the degree is going to be increased. According to that, we'll keep their x. Okay. So these are some proof. He is solving some example, I think, how this could be converted. This is again, this is a separate, you can break it out 3 plus 2, right? This is 3 plus 2 kind of this middle part, and this is x plus 3 and x plus 2. And then c upon x plus 2 and d upon x plus 3, you can take it and separately make. This is how you can make. To do the second problem here, you can just see this is are the separated one by one, assuming to be. If you will do here, I think the professor is did this one. Okay, he is doing for a square the root of it. So I'm going to be the complex number. So that is a good thing that he is doing on the complex also. So synthetic division of all of you know that this is a synthetic division. All of you know the synthetic division. All of
Yes,
you
sir.
know synthetic division of the
Yes, sir.
Yes, sir.
is this is how we'll do. Very. Let me do one example on it. So let's say I have a polynomial px of this case x cube plus 2x plus 2x square plus 2. Okay, and qx is this one. Let's say x plus 1. Okay, so I want to divide. So I want to get px by qx. Okay, I want to get it. What is going to be that? What is the quotient of what I want to get it here? So synthetic division is, you can write like this: x cube plus 2x square plus 2, and this is x plus 1. So whatever the degree here is, degree is of x is 1, right? And the highest degree will take of the term here on this part, and just divide the degree, or mean to say, you can, what is the meaning of behind it? We are doing here x cube by x, so you'll get here x square. The highest degree of this term, the highest sorry, highest degree of the term. We'll take that term which have highest degree of this side we'll take, and then divide it. So we'll get the x square here. Okay, we'll get here, we got here x square. Now you can take this x square and you can multiply, this will get x cube, and then here we'll multiply, it will be plus x square. Now as the division, we subtract generally, this is how we'll do the subtracts. So this will be cancel out, I will get here, this will be just x square, right? So this is x square plus 2. Now let's do the division of the highest term is this one. This, whatever the remainder we got, the highest term is this one. And here is again, we'll take this x. And now we'll do the x square by x. We'll get here x. So here that means plus x is there. Now we'll take here the x. Now you can take this x to multiply both terms. So we'll get here x square plus x. And now subtraction will do, so this is going to be cancel out, and you'll get here minus x plus 2. Now the question is still how means how much we'll do this, how many times we'll continue it. So here is, if the degree is lesser than the degree of this one, so here is degree is 1, here is degree is 1, so again it will still will do the division. So if you do it here, minus x by x, the highest term is this one, highest degree term, so you'll get minus 1 here. So here is minus 1. So minus 1, this is minus 1, and this is minus time minus 1, which is minus 1. Now we'll subtract, so this will become plus and plus, and now this will be cancel out, and this is going to be 3. Now we cannot do the division. Now this is going to be the remainder. The reason is the degree of this term is now lesser than the degree of this. Okay, so we can now stop and we can write like this. So our p by q is going to be x square plus x minus 1 plus 3 upon the x plus 1 here. This is what you get. Previously it was, so if I will write properly here, it was this one, x cube plus 2x square plus 2 upon x plus 1. This is what previously, but we have solved it and wrote like this. This is what we do. So this is the synthetic division of the polynomial of, this is how. Okay. So many of you know it. If you don't know, then this is what we will do. Please stop me if you are not getting, okay, so that I will do some another example to understand this division. Okay. Okay, this is the rational or doing the rational part. Okay, please just stop me if I'm not getting or anything as I'm missing, or you want to do something for me. That means I want to say to do something. I will write that. Okay, if I'm not getting anything lecture, you can just let me know. Okay. Is this clear? Reason is clear. This rationalization.
Yes,
Yes,
sir.
sir.
Okay. Let's see the trigonometric now. This is a small lecture, but interesting. So I will start now from the last time we have seen the sine function, how it came. So I will start again from there. No? So we have this trigonometry is generally, you can say, started from this case only. This is, let's say this is theta. This is angle, at least You know it. This is the angle theta, or let me write like this even. Okay, sorry. This is theta. Okay, let's say I'm saying this is 30 degree. Okay, this is 30 degree. Okay, let's say I have this A, B, and C. Okay, so what is the case here? So if you see here, the ratio B by AB, sorry, BC by AB. If you see here, let's say I'm writing here, the base is B, this is height, let BC, BH, and let's say this is alpha. Let's say for the timing, this is alpha, hypotenuse. So if you see here, B by C, B by BC by AB, which is going to be, if you see this ratio, which is H by AB, which is alpha. Okay. For the time being, let's say this is what I have. Now I am changing a different picture. In the different picture, let's say I'm making, this is here, this is again theta, but I'm making slightly bigger. Okay. So let's say this is A prime, B prime, and C prime. This is theta again. Okay. Now theta, this is 30 degree again. So here, if you see here, alpha in here is, let's say this is alpha prime and this is H prime. So it is from the picture, at least it is very much clear that alpha prime is greater than alpha. H prime is greater than H, right? It is very much clear, at least from the picture. But if you do again this ratio, BC by AB, here is B prime, C prime, A prime, D prime, alpha prime, this is going to be, or maybe H prime upon alpha prime. This ratio is whatever the ratio you are getting, this ratio is going to be same. This ratio is going to, this is what the thing is, that in the case of right angle triangle. Okay. So why it is so? Why this is? Anyone thought why it is so? Why this is? Anyone can answer something about it? Anyone can say about why it is so? Why it's happening? No. So there is a theorem related to it that is not needed here even. The same picture, in the case of same picture, the angles are two angles at least same, then it is going to be something. There is a theorem related to that. I mean to say here why I started. See, the degree is same in the both case here at least. Okay. So maybe we can think like this also. Let's say this is theta. Okay. Maybe theta of this case is also, I'm saying this is some theta prime. No? So I mean to say we can start thinking angle as a variable also. Okay? We can start thinking angle as a variable also. So can we? So one thing is there, this height, okay, and this hypotenuse, this one, this height and this hypotenuse, if we change with respect to this theta, it may different. Here is the angle is same, then in that case the ratio is same, right? When angle is same, the ratio is same. But when angle is different, then ratio is may not going to be same. So it kind of, so from here is we have started thinking that what is going to be the ratio in this case always when we are changing the theta. So from here there is a thing, we starting theta is as a variable, and there is a word sign, you can start sign. Actually not even this is what is started, even started from the circle. Still not going to go so deep, but this is the idea about this sign, that okay, I started by sine. Okay, so I'm thinking sine as a variable. Again, I can write even sine x. So in the generally in the angle case, we generally write sine theta. So here the meaning of sine theta is, now I'm going to take as a variable, but here the meaning of is that height by this hypotenuse. Okay, it's alpha. So even I am changing the theta, it's will change the this one and this one. Okay, but if it is the same for both case, this sine theta, which is 30 degree, is going to be fixed. So here you can see if it is a making, if you have a right angle triangle. Okay, however you are taking the big triangle, this kind of, the ratio is always going to be same. Okay, but in the case of I'm changing theta, then it is the ratio is going to be different. That is was the meaning of it. So here the sine x or sine theta is in the with the same case I am thinking it as a variable. So this is also going to vary. Okay, height and alpha according to that. So this is started, from this way. See how much this will go if you start thinking of this angle. Let's see that how it is. This is 45 degree. Let's say I'm making an angle 60 degree even. Let's say this is, or maybe of this is 60 degree. This is 60 degree. See? So if you take the ratio of it, it will give something. Okay. But what is going to be the case when it is 90 degree? So height is, let's say, this one. What is going to be the case when it is 90 degree? So it will not intersect here, right? This is not going to be intersect these two. But we want to get that ratio. So here the idea is started saying that okay, sine 90 degree. What is going to be the sine 90? So I am doing from the right angle triangle. The idea is started from mostly from circle. Okay, started from circle. So here is actually the meaning of, suppose this is the circle. So if you see it here, this angle, this angle, this angle, slowly this angle. So whatever it's becoming this height now, with corresponding to this height is corresponding to this height, this height. This is how it's started. So sine theta here, sine 90 is actually meaning of one. So this is how it's started, sine x. So if you think it here, sine x. Sine x function is generally, will, this is what the meaning of in the right angle triangle. Okay, but sine x have some, so this is a function, and the graph of function is now this one. Like this function is get at most the value 1. Okay, and at 0 this is 0, and sine 30 is going to be 1 by 2. Sine 45 degree is going to be 1 upon root 2. Okay, sine 60 degrees. What is the sine 60 degree? Anyone can tell what is a sine 60 degree if you gone through with the lecture? No?
3 by root 2. Root 3
Sorry?
by 2. Root 3 by 2.
Root 3 by 2. Root 3 by 2. It is going to be the whole root or just root 3?
Just root 3.
Just root 3. Yes. This is going to be this one. Okay, and then sine 90 degrees 1. Okay. So graph is going to be like this. So yeah, see, one thing I missed, that this degree is given, this value is given in the degree, but we can convert this degree in the real number form, that is called, in radian. Convert this in radian. And here, to convert any degree to radian, we generally do pi upon 180. Okay. So here this pi value is something. Okay. This pi value is generally, at least, at I think 10 or maybe 12, generally pi will say 180 degree also, the meaning of it. But this pi have some different notation. This is used to convert any degree into real. This 90 degree, this is going to be pi by 2. So here it means here is somewhere 90 degrees. So here is pi, and somewhere here is pi by 2. So here is at most value will attain, and then again pi, it will be the 0. And the same for negative side also. So here this sine function is, see, this sine is started from, circle generally, that is what I am saying. So it is a periodic function. It have at most value 1. And this is what the case is. It will be, 0 to 180 degree, we think here. So whenever we want to say from 0 to, or maybe, 180, 0 to 180, or maybe generally we'll think our sine function from minus pi by 2, because at pi by 2, which is 90 degree, the angle side, and it have at most 1. At minus pi by 2, it have the at most negative value, which is minus 1. So generally think our function between minus, sine function between minus and 1. So sine function will assume the value, okay, between minus 1 to 1. Okay. This is what the idea here. So here is axis, you can substitute any angle, and according to that it will give the one outputs. Okay, so here is whatever the angle you will get, it will give the one output. Okay, it is not going to be the different, or this sine function is between minus pi to pi, is actually a proper function. Whenever you say sine whole 160, this is not a function. You have, whenever you are saying sine uh, sine or maybe you want to say not a function, you want to say 1 function. If you remember it, what is a 1 function? In that case, it is going to be a 1 function between the interval minus pi to pi by 2. Otherwise, rest all, see, again it started getting back to, the same value here. These are the output value, right? So value is going to be, at the input are different, but outputs are now same going to be. So sine is a periodic function. It will, the period is, you can say pi. The period is pi. Then again, it will start getting the same value, 0 to pi. You can say this is pi here. And generally we think our sine function between minus pi by 2, pi by 2. And these are some sine values. Okay. Sine 30, sine 0. So here is sine 0 is 0. Sine 0 is 0. If you see why it is 0, sine 0 is 0. So it is kind of you making a circle here. See, this is the angle. If you think this is a theta, and theta is your 0, means your this line is not lifting. It is exactly on this. So if you think there is no height, height is not gaining. Okay, and this hypotenuse is going to be same, but it is not getting any height. So that means 0 by alpha, which is 0. So this is how the values are also generated. Okay. This is how the values are also generated. So mostly even the meaning of this sign is between these two cases, the value is evaluated, and slowly the sine function is developed. Okay. So sine 0 is 0, sine 30 is 1 by 2, sine 40 is 45 is 1 by 2, 1 by root 2, sine 60 is not this one, root 3 by 2, and sine 90 is 1. This is how it is. Same way as we are thinking the sine, we started thinking this height, no? This height. Can we think this base also, which is b here? Can you start thinking b by alpha also? Okay. And this is the case, generate cos. Okay. So again, the ratio is going to be same with the same degree. So this is how the cos function is also came. Okay. And there is a relation also. So I'm not going to now say about what is the cos. So you can say, yeah, this is how the cos function started coming, and started also. And the cos is have the same idea. There is a relation between sine and cos. Can anybody, if you have gone through with the lecture, at least can tell what is the relation between sine and cos? Sin x is equal to, what is the relation between cos, sine and cos? Anyone can tell, or anyone to repeat, say to repeat this sine function, cos function again? Anyone have remember relation between the sine function, cos function? No? Okay. So here is, as the sine is developed from height, height, and then this hypotenuse. Okay. Similarly, cos is also developed from base upon this alpha, b upon alpha prime. So here is b prime. Okay, so same meaning is there. Okay, same. There is not difference, I will say. So cos is nothing but your cos x is nothing. If it is a cos 30 here, if I am taking this picture, so cos 30 is b by alpha, okay, base by this hypotenuse. Okay, this is what it is. So can anyone tell what is the relation is happening with this? Can we start from the picture itself, the relation between sine and cos? From the picture, any idea? Anyone is getting? No? There
They
is a
are
problem.
complement of each other.
Sorry?
They are complement of each other.
So here is actually what is happening. See, we can think this is 90 degree, no? The angle of the sum of these three angle is 180, of any triangle. So here is, 1 minute, my battery is just a second. Very interesting. See, we are going to see, and it will tell you the relation. Okay, so see, here is what's happening. We know, right? This is already 90 degree. In any triangle, the sum of the angle is 180. So this is already right angle triangle. So this is 90 degree. This is 30 degree. So this is very much clear that this is going to be 60 degree. Right? This is a 60 degree. And if we think our right angle triangle, thinking to be of this case, okay, I'm making a very I'm making a same triangle, but the different picture. See, this is the height I'm writing here, and this is the what? This is the base, and from base to height, this angle is 30. See, this angle is here. This is here I'm making. I just reverted. So here is I just flipped. Here I just flipped. So this is your B. This is H. Okay, and here is your angle A, and here is your becoming angle no C. This is your B here. So I just flipped 90-degree. See, now it's whatever the here case, it's our the case is that okay, this is 30-degree here. Now we can start thinking this as a, so here is already 60-degree we have calculated. So can we think this sine 60, assuming to be this is the height and hypotenuse is going to be same here. So sine 60, this is the sine 60 now. Sine 60 is b by alpha, right? Sorry, yeah, b by alpha. And here is just now we'll calculate it. Sine cos 30 is b by alpha, right? Here we have just seen sine 60 is b by alpha, but here is cos 30 is also b by alpha. What it mean that sine 30 have the same value as sine 60. See, this is what the interesting thing. This is what the interesting thing. We slightly flipped here. This is our original picture. We slightly flipped to slightly flipped. I mean 90-degree. We flipped it, and this is what the picture is coming. And we know the theory of sine. And from the sine, we develop the cos theory. No? This is what it's happening. As I said, from base by hypotenuse this alpha, but this is nothing but the sine 60. And this is what the relation. This is what you want. So can we write this sine 60 as this case also? So we got this 60 from how? Sine, right? We got 90 and then subtracted 30, then we got, right? Sine 90 minus 30, then we got 60. So this is what the interesting relation here. We slowly develop that relation between sine and cos. So sine, so this 90 degrees, we know if we change into radian, we change already. So this is going to be 2 and this is pi by 2. So we can say pi by 2. Okay, and this is 30 is nothing but cos 30, right? This is what it is. Just now we are looking the same thing I'm making. When if you want to change the 30 into radian also, you can change it. But to make the distinguish, that's why to make the distinguish with the 90 and 30, that's why I change this pi by 2. Okay, so that you are able to visualize it. Otherwise, I can keep the same 90-degree or pi by 2 or whatever. So sine pi by 2 minus 30 is cos 30, right? This is what the relation we want. And we slowly develop this. How we got this? This is no, I'm not doing anything. I just use the this triangle, and from there I am developing the relation. Sin pi by 2 minus 30 is what? So simply we can now develop that sin pi by 2 minus theta is cos theta for any general theta. Interesting, no? Just slowly flipped and we got some relation. I think many of you know it also. Maybe many of you may be bored. I don't know. You can react on it is good or whatever. Okay. So this is what the sine relation. Can we think? So we thought this pi by 2, no? We thought this pi by 2. Can we think of this case also? What will happen of this case? Sine pi by 2 plus theta. Here is negative. So we know, okay, this is what. Can we say about, can we think about sine pi by 2 plus theta, what is going to be? So to say that we can slightly do the operations change, okay? I'm not going to do anything. I will do, I use this one even, minus theta. And we know that, okay, this is the cos. So cos of minus theta. Right? Cos of minus theta. What is going to be the cos of minus theta? So cos of minus theta is going to be what? So Also, let me back to the first the graph. It can we relate from here with the graph also, and then easily can answer. So see what is happening here. So cos, so here we got cos theta is nothing but pi by 2 minus theta. So can we graph? We know the graph of sine. No? We know the graph of sine. This is here pi by 2, let's say, and this is here minus pi by 2, and here is minus 1, and here is plus 1. So it says that cos theta is nothing but just flipped of 90 degree. So okay, this is our sine graph. Can we flip it with the 90 degree? So how we can flip it here? Let's flip it in the graph itself. It is interesting. Okay. So if we flip it, what's happening? So if we flip, so what we can do? So cos 0 degree. Cos 0 degree, what we can think? Sine pi by 2 minus 0. And which is nothing but sine pi by 2, and we know this is 1. Sine pi by 2 is 1. So that means cos 0 is actually 1. So if we're giving the input here 0, it is going to be 1. And this is what the flipping thing is happening also. See, this is your 90 degree, no? This is your 90 degree. And we just slightly flipped it. So this will be just shifted to here. Okay. So actually this is going to be, this is how. Sine 0 is going to be 1. And if you think about cos 90 degree, which is nothing but sine pi by 2 minus 90 is the same pi by 2, which is 0, sine 0. Sine 0, we know that it is 0. So at pi by 2 is going to be 0. So can we match like this? Because the same relation is there. So at pi by 2, where is your pi by 2? It is 0. And at what is going to be at minus pi by 2? What is going to be at minus pi by 2?
It's -1.
Is this minus 1 or just 1 or anything? Others can also answer. Anyone else want to answer?
It's, it's -1, sir.
That is minus 1. Okay. So the how then graph is going to be?
Sir, you are asking about cos of minus pi by 2?
Yes, cos minus pi by 2.
Sorry, sir, it would be 0.
It is going to be 0. Okay. So many of your answer minus pi by 2 is minus 1. So anyone can fix it? What is going to be sine and cos? Okay. So let's see that how it would be. This mass will give more idea. We'll fix with that. So if you draw sine x, See how, what is this? How the graph it is. And let's see the cos. So the green one is our cos and the blue one is our sine. So see, this is at 0 is 0. And now here is your our pi by 2. So it have, for sine it is 1. And for minus pi by 2, see here it is minus 1 for the sine one. If you see the green one, here it is minus pi by 2, right? See, it is 0. This is 0 here. That is what I was saying, no? Flipping is here. And also I roughly made the graph at how it is. So at 0 it is 0. At here it is, sorry, at 0 it is 1. At pi by 2 is 1. Okay. But our graph is continuing like this. Okay. But here it is 1. This is also sine. Cos is also going to be a bound minus 1 to 1. So slowly it will not go beyond of it. It will back to here. So where it will back? It will back to at minus pi by 2. And it will back to minus pi by 2, which is 0. And where it will attain then minus 1? Anyone? Where it attain the minus 1? Anyone can answer? Where it will attain the minus 1? Okay, let's evaluate from here itself.
It will be pi.
It will be pi. Okay. So it will be pi, it will be again at here, it will reverse back to, it will be, and slowly see how it is now back to here, it is going to somewhere pi. So where it is going to be? No, I just mentally wrong here. Where it is going to be now? This is here. It will go till here is. After pi by 2, what is going to be the next? Then 180. Then pi by 2 plus pi by 2, which is just pi, or mean to say in degree, if you think this is 180 degree. You can convert that. So cos is also going to be between minus 1 to 1. And the very thing is that this will again back to 0. So here after pi, I said, no, this, the proper interval is, this is pi by 2. So at here it is going to be pi. So where it attained the maximum, which is minus 1. And again, next pi is, which is pi plus pi by 2, which is, if you degree, you will think this is 270 degree. So which is 3 pi by 2, which is again 0. So if you think our graph for cos, we generally think from, this case, making of cos is a proper between minus 1 to 1. So where we'll think here, at 0 it is highest, and at minus pi it is the lowest. Sorry, at pi it is the lowest, minus 1. Here minus 1. And this is here 1. So see how it is flipped slowly. So it is flipped to slightly here, and it will back to here. So see how it will go. This will be like this. So even properly thinking to be minus pi by 2, this is our, if you see it, this is going to be like this. Yeah, it is generally thinking to be 0 to pi minus, sorry, here 0 to pi. So this is how it is. This is what the flipping is happening. So see, this will be here, and this will be shifted to here, and this will be shifted to here. Slightly flipped, and this is what it's happening. As this region and shifting is that, see how I, because adding and shifting is there, no? Pi by 2 plus theta, pi by 2. So slightly shift is there. Shifting in the angle it's happening. Sorry, flipping, and the shifting is because of, plus minus is there. That's why it is just a. So see, these are ideas actually. The main thing is that how it's done. So I want to tell you the idea. So these are the relation. Actually, relation is developed slowly from here. The relation is cos theta, how it came, or cos sine theta plus pi by 2, sine pi by 2 minus theta is going to be what, sine what is going to be. So there is a, relation on making. So slowly these all theory, these all practice is done, and then it said that sine theta and cos theta is positive this side, and here is sine theta, and what is it, this here is sine and cos is positive, we know, right? Sine and cos is positive. Here is sine is positive, here is tan is positive, and is sec and cosec is positive. Sorry, sec and cos. Okay. And here is sine is just positive. Tan and cot, the inverse of cosec is positive. So this is how the slowly, these theories are developed slowly. You can remember these tables. Otherwise, you can remember by this way, sine pi by 2 minus theta is cos theta case, and sine pi by 2 plus theta is going to be what? Minus cos theta or just cos theta? Anyone can answer?
It will be only cos theta.
Sorry, it will be
Only cos theta.
only cos theta. Okay. Anyone else? This is going to be minus cos theta or cos theta. Interesting to remember it. Anyone can answer before to search it. Minus or plus? This is going to be plus. Why it is so? Ever you think that why it is so? How or why it is happening? Can we develop it from the picture? Here I made table, right? So here I made table that okay, all sign is positive. So whatever the theta I will substitute here, it will give the positive. Whatever the tan you will give, that is going to be positive. Or this is sine cos, both is positive. Here is second inverse of that is cos, and other things are positive. So whatever the tan theta is going to be in that, that is going to be positive. So here is not negative, here is positive. So actually these all things are there. You can remember, even generally you can remember it. The other things are, other than the sine cos is also, let's start with tan also. So these are some things are there. Similarly, the sine pi is there. Pi minus theta, again this is going to be sine theta. Cos pi, or maybe sine, again it is following where it is here, and it is again the same signs could be. So you can remember this all. Sine pi plus theta is going to be minus sine. You can remember this all slowly. So I'm not going to write it even. So you can remember this all. This is just remembering one. But these all developed from this trigonometry, this right angle triangle and this circle thing. Okay. There is a relation between cos. Again, also you can then cos theta minus, which is just sin theta. So you can remember all this, how it is. Okay. So these are the, otherwise we'll not able to complete this one. So there is another trigonometric function, that is tan. Tan is, again, it is generated from the same table. In place of thinking base and hypotenuse and this height, in case of that we can think the ratio of base and height, and this is how it is developed. Tan theta is height by base, and then this is nothing but a case of sin theta upon cos theta. This is also the relation, from relation it's developed. So tan theta is nothing but your sin theta upon cos theta. And there is one thing is that cosec theta and the sec theta and the cot theta. So cot is there. Cos theta is nothing but 1 upon tan theta. So other things you can remember from. These are the three important trigonometric functions: sin x, cos x, and tan x. Okay. These are three things important. The others are, you can, cot is nothing but 1 upon tan. There is another sec theta, which is nothing but 1 upon cos is there. And there is a cosec also, cosec theta, which is nothing but 1 upon sin theta. So these are developed from, cos. And these values also you can evaluate it, or table values you can evaluate from the same sin, cos, and tan theta. Okay. So these all you can remember it. Okay. So I mean to say that I want to tell you the how it came and what is the relation, how the relation is started. The main thing I want. The other theories you can, these all formulas you can remember easily. It will take some time, but you can remember easily. You know already it. So, but this is how it's developed, and this is what something about the graph. There is a tan graph if you think. So tan graph is, let's say here is pi by 2 and here is, now I am going to beat the speed. So here is pi by 2 and here is pi by 2. So tan values, assume it is not bounded to be -1 to n, it will bounded, it is not bounded even. This is minus infinity to tan x is going to be the any value it will attain to positive infinity. So here is actually, this is what the tan is there. It is also periodic, but this is also periodic, but it will be, the values are repetitive, or period with respect to the pi is period, and value is going to be the same, repeat with respect to whatever the value is attending here. No, these are the values attending. We think here the 3y by 2. Okay, at pi it is 0. So it is going to be the same we have. We have the same. So it is a periodic again with the pi, and it whatever the value attending between minus pi by 2 pi by 2, here is between pi and 3 pi by 2. The same values it will take. So these things you can see it lecture. I want to just discuss a bit about it. So these are the some trigonometric function. Okay, and some of the values is also we had discussed. One important thing is we want to talk about the inverse of trigonometry. Inverse of the trigonometric function. So one question arises before we start the inverse. What is the inverse function? So I want to now focus on here. That's all it is about the trigonometry. You can remember the things easily. Okay. These are just formula. Okay. The development theory is this one. So, but the first thing is, what is the inverse function? What is the inverse? So let's say I'm writing fx is equal to, let's say, x plus 5. Okay. So let's say I'm saying f2 value is 2 plus 5, right? In expression we substitute, which is 7. Let's say f7 is, or let's say f9. What is f9? 9 plus 1, which is 14. Okay. Or let's say f10, which is 10 plus 5, which is 15. See, I want to show something that if it is true, 2 2, you got 7. If you are substituting 9, you got 14. If you are substituting 10, you are getting 15. Okay, this is how it is. But suppose the case is, can we get a function? Okay, can we get a function of this case that I will substitute this 7 and I will get back to 2? Can there is any function exist? Is there any function exist? Like here I am substituting 9, I am getting 14 here. Okay, is there any function wherein that I will substitute 14 and I will get back to 9? I will get 9. Is there any function g where I will substituting 7, I will get 2, I am substituting 14, I will get 9, I will substitute 15, I will get 10? Is there any such function exist? The question is this one. When it will exist? Is there any function first exist? When it will exist? The question is this. So anyone can answer. If you have seen from somewhere, is there any such function exist always? Or do we need to give some condition? We have to impose some condition on the function so that we'll get always such function. That is the meaning of the inverse function. Means g is here is a function which is actually the from output to taking the back to input. I am substituting the outputs and I'm getting the inputs, and that is your inverse function. Is this clear? What is the inverse function to all of you?
Yes.
So the question is, okay, so inverse is clear. So but the thing is, when this inverse will exist, the question is this one. When we can say the inverse exists? Is there a condition needed or always exist? So let's see two example. Let's understand by two example. Then when easily you even use yourself, you will conclude. Then when it will exist? The first thing is that let's say I have one example function f1x, which is of even the same fx plus 5, and the second function fx is equal to x square. Okay. Let's say I have two functions. So when I substituted 2 here, I got 7. When I substituted 9 here, I got 14. When I substituted 10, I got 15. Similarly, single value will. Again, let's say I'm substituting now again. Let's say I'm here is separately here substituting f1 it is. F minus 2, I will get 3. F minus 9, I will get minus 4. Right? Yes. F minus 15, I will substitute. I will get minus 10. See, this is these values are different, right? I'm just changing the sign. I'm getting different terms. Let's see it here for this case function. I'm substituting 1 here. I got 1. I substituted 3 here. I got 9. I substituted 5. I got 25. But see also, I substituted minus 1 here. I also got 1 the same as this one. But 1 is not same as minus 1. Input is different, but output is same. Here, this one is different with respect to this one, but output is the same for both. I substituted minus 3, I got the same 9. I substituted minus 5, I got the same value 25. But here the case, see that I substituted the negative, the same negative with the negative, I getting different. So this is what the thing is important now, and this is what the inverse needed. So in this case, our actually inverse is exist, and we can explicitly get the gx, which is you can say gx is nothing but x minus 5. If you do x minus 5, I am explicitly got this. By random I got this. Okay, I will tell you how I got, but by random I got this. And see how it is. Now I substitute, I said no, substitute 7. So substitute 7, it will be 7 minus 2. So 7 minus 5, which is 2 here. See, this is the input one I got here. I substituted 9, sorry, I substituted 14, which is this one, output 1. Now 14 minus 5, which is 9. See, the input one I got here, 9, 9. Similarly, if I substitute g of 10, which is 10 minus sorry, I substituted 15. No, I need to substitute the output. G of 15, which is 15 minus 5, which is 10 here. See the input one I got here. Okay. This is what one thing I by random I got gx. Okay. By random I got gx. But what about this case? Let's see it. Is there any g? Okay. So that I will substitute and get the same input. So let's say I'm writing root of. Let's say I'm writing some by random I got, okay, root of x. So we know that root of any function is plus minus both. Okay, so this is one thing. So let's do it here. I have substituted 1 here. So I got plus minus root of 1, which is plus minus 1. So two value I got. But which one of this one? Or let's say I'm just saying not plus minus 1. I'm just saying I'm taking the plus 1. Okay, so plus 1 I root of plus 1, which is 1. But 1 I am getting with the minus 1 also. How we can say the minus 1? So how I'll get minus 1? So this is the problem here. Problem is what? Can anyone tell in your word what is the problem we are getting? Can anyone tell what is the problem here we are getting for the inverse of the left one f2 and for here for for f1 and f2? So here is I missed to the this is f2 all. Here is g1 is, let's say this is g2, this is g1. What is the problem here happening? Anyone can answer it? That would be really good. What is the problem here in your word? Whatever you are in is coming your mind can tell. No? So problem is for the when you are getting same output for different input. That is what the problem is. I am getting the same output but substituting different input. I substituted here 1 and here substituted minus 1, but getting the same output 1 and 1. Here is 9, here is 9. The inputs are different but same output. So problem is with the when we are getting the same output but the inputs are different. Here is inputs are different and outputs is also different. We are not getting the same. So that is the imposing condition. A function is inversible or inverse exist when the function is, so this type of function is called 1 1. Okay, the function is inversible when the function is 1 1. Okay, there is some childhood, you know, the onto word also, but the main case here is if the function is 1 1, then we can say the inverse exists, because onto we can make, we can by bounding it, by giving some bound, we can make it onto and then can say the inverse exists. So main thing is 1 1. 1 1 case means I am giving the one input and getting the one output, not same output but with the different input. I am getting here, I am giving the two different input but getting the same output. That is what the case, and that is the imposing condition on the inversibility. I want to inverse or to get the inverse of a function, saying to be the function is 1 1. So that is what the inverse means. Inverse, I hope all of, so you can write this f1, this g1 is your nothing but f1 inverse. Generally we denote it like this. G is denoted as a f inverse, f1 inverse of. So inverse of f, if you have function fx, we generally denote it like this. Okay, this is not the power, this is a notation. Okay, this is not the meaning of 1 upon fx. Okay, so don't be confused with this sign. Okay, this is telling you the inverse. Okay, not for the power. So whenever of this case, so our trigonometric function is the problem now, because this is a periodic and we know that okay, it more attend at most between minus pi to pi 2, and let's say I'm saying for whole hour. The problem, if I'm saying what is going to be inverse of sin x for whole hour, we cannot say. Then yes, needed. That's why I said no, I will bound our function between minus pi by 2 and pi by 2. In this domain, our function is 1 1. and in this domain we can say our function is inversible. That is what I said. No, I can give the bound on the domain and make it 1 1 and onto. So I am bounding the domain here between minus pi by 2 and pi by 2, and in this domain the function is 1 1, and so that we can talk about the inverse of sin x. Similarly, inverse of cos x also by giving some bound between 0 to pi. For tan also, minus pi by 2 to pi by 2. You can bound over, you can get the inverse. This is what the meaning I started. So is this clear? The first thing is this clear to all of you? With
Yes,
the
sir.
inverse and the inverse of the sine, how it came. Our sine function, cos function, and tan function are not one function, but we can bound the domain, and within the domain we can make it a 1 and talk about the inverse of the trigonometric function. Okay. So many people have, even I was there in when I was in 10th standard, or maybe in 8th standard or 10th standard something. Then it's, inverse came. That time I thought how the sign is not 1 then how it could be, but by giving the bound we can inverse on the domain. Okay. This is really interesting, and maybe it will a doubt ever of someone, but I'm not sure. It was a doubt of for a longer time for me, but slowly I got it. So see how what is here. It's that is what the professor is telling. This is not a, this notation and this different notation is different, and this is what the inverse of the sign. So see, this is what this is a within some interval I can bound it and get the inverse of it. Sine inverse x is minus 1 to 1, and then output is the degree. If we talk about the inverse. Similarly, we can talk about the cos also and the tan also. So professor is just giving the introduction of it. So even I'm not going to go so deep. See the tan also I said no, between minus pi to pi I can give. So I can bound between minus pi to pi. So range is, I said, minus infinity to infinity. So here for inverse, domain is minus infinity to infinity, or r you can say, and the output is going to be between the minus pi by 2 and pi by 2. So professor is just introducing the inverse. So that's it. Yeah, some shortcuts is there. Cosec is x is nothing but sine inverse of 1 by x. Tan of cot of minus inverse is pi by 2 minus tan inverse. These things you can, or within the domain, this could be, you can remember this all. This is interesting. Sometimes it is usable. Okay. So it's just introduced and some giving theorems, or sorry, some formulas, you can remember it. But this is what the inverse of trigonometric function. This is not a different, this is a small portion. That's why it is a small lecture. When you not see the more thing about it, but this is what the idea that, okay, we will bound our trigonometric function, and when then we can get the inverse of it, and all other things are there. Okay. So interesting. The inverse is actually and really interesting. Okay, and this is how that much lecture I want to cover today. And this problem is that contains the problem. You can see the problem. The derivative of trigonometric and hyperbolic inverse of all other things we will discuss in the next lecture. So 3 lectures I think there, 6, 7, and 8 remain is to me. Okay. So my question is this clear? Whatever we discuss was interesting? Still doubts are there?
No doubt, sir.
Interesting, no?
Yes, sir.
Okay. Is this understandable? We discuss
Yes, sir. It's clearly understandable.
silent, but I try to how much possibly I can tell you, that much I try to tell what are the things in layman term. Okay, that's all. Okay, thanks everyone for joining. And anyone want to say something, any feedback want to give regarding the session, or anything want to say, any doubt is there, please let me know. I'm here to discuss it. Okay, fine. Thanks, Suryan. Thanks for joining. Good night. Good night
Thank
to
you,
you.
sir.